Alright, so today I'm going to be explaining another extremely important paper with the title Graph Neural Networks Gone Hogwild. This ICLR paper in 2024. Message passing graph neural networks would appear to be powerful tool to learn distributed algorithm via gradient descent, but generate catastrophically incorrect predictions when node update asynchronously during inference. This failure under asynchrony effectively excludes these architectures from many potential applications. So we explore why this failure occurs in common GNN architectures and identify implicitly defined GNNs as a class of architectures which is provably robust to partially asynchronous hogwild inference, adapting convergence guarantee from work in asynchronous and distributed optimization. So when node update asynchronously, messages received from neighbors may be out of date, and the effective architecture of GNN diverges catastrophically. So they talk about partially asynchronous algorithms, that this assumption there exists an integer such that for every node I, at least one of the elements belong to T sub I. Explicitly defined versus implicitly defined GNNs. And then they talk about fixed point GNNs and optimization-based GNNs. And optimization-based GNNs are an important special case of fixed-point GNNs, obtaining node embedding by minimizing convex scalar valued graph function with respect to aggregate graph node embedding H, where theta are parameters. So we assume E sub theta is separable per node, with each node computing its contribution to E sub theta using local information. That is, E sub theta can be expressed as this. Here, E sub theta depends only on information from ith neighborhood. So due to dependence of this E sub theta sub I on local information, gradient-based minimization of E sub theta can just be expressed per node via message passing. So executing layer updates during GNN is typically performed synchronously. In the general asynchronous update in equation 2, it is assumed that node I has access to all of the values required for performing update. In general, these could be obtained, for example, by providing node access to a shared memory structure which contains. However, in this work, we are interested in decentralized distributed asynchronous. First of all, this AI that you are talking about is super elementary. It is still its infancy. But our brain, if you look at the brain, first of all, you see the spiking. It is asynchronous. It has a temporal graph. It's dynamic graph, I mean. It has temporal structures because of the timing of the spikes is different. It is directed. I mean, from childhood, when you are born, it is directed. So we call it synaptic polarity. But in AI, everything is continuous, is carbon footprint. If you look at the ChatGPT, the carbon footprint that this company OpenAI generates is huge. And maybe it in the order of all the budget of Iran. So it's huge. And AI still is infancy, you know. Everything is artificial. And in terms of power consumption is terrible. I talked about carbon footprint, which is terrible. So that's why we need to work on a spiking graph neural network, asynchronous like this great paper. We should work on temporal graphs. We should care about directed graph neural networks as well. And they talk about compositionality, equivalence of graph neural network. And there are many things that if you work on these research areas, then we can move AI a little bit more. Otherwise, in the next 10 or 20 years, we don't have anything. But there is a good pragmatic approach, which is neurocomputing. And there is a journal of neurocomputing, and this research of brain inspired is very good. So this paper is in this direction. I think everything as a asynchronous thing. And they generalize it for different multi-agent tasks. And they did experiments that you can see here. So it's an asynchronous GNN training, which is a new line of research, which is very bio-inspired.